Welcome to the E-Padhshala lecture series in computer science. We are looking at the computer architecture course. So this module is on multi-core architectures. So the previous module we looked at one case study, namely Intel's multi-core architecture. So this module is to discuss the salient features of two different styles of multi-core architectures, namely Sun's Niagara and the IBM's Cell BE processor. So when you look at the Niagara processor or the UltraSPARC T1 processor, basically they were actually brought into picture because they wanted to serve commercial server applications. So when you look at commercial server applications, there is a lot of thread level parallelism available in such applications. There are a large number of parallel client requests that come in, and the instruction level parallelism is not too much in these cases. It is very low in the case of commercial server applications, and because of that you might have high cache miss rates and you may have many unpredictable branches and you will have frequent load dependencies. So commercial server applications are very high on thread level parallelism and they are low on instruction level parallelism. So the goal of the Niagara processor, or it is also called the UltraSPARC processor, was basically to serve commercial server applications. And the other factor that was basically predominant among the motivations for this architecture was the power, cooling and space. They were basically looking at commercial server applications which are major concerns for data centers. So these were the two major requirements of when this processor was brought into picture. So the Sun solution for these requirements was the UltraSPARC T1 processor and UltraSPARC T2 processor, which was codenamed as Niagara 1 and Niagara 2. And according to Sun of those days, this was the highest throughput and most eco-responsible processor ever created. Eco-responsible because they were also looking at reduction in the power consumption, which is definitely going to be more eco-friendly. It is obviously a fine multi-core architecture which supports fine-grained multi-threading within the core. We also discussed about what fine-grained multi-threading is. Fine-grained multi-threading is one way of multi-threading where every clock cycle the processor switches to a different thread of execution. And as against complicated pipelines or deep pipelines which try to exploit your ILP too much, here we have very simple pipelines. So there is a small L1 cache, there is a shared L2 cache, and the main metric was performance per watt. People were only interested in the performance per watt. So this shows you the die of your UltraSPARC T1. So the main features of this processor are 8 64-bit multi-threaded SPARC cores. SPARC stands for Scalable Processor Architecture. SPARC was the main processor that was introduced by Sun, and most of these processors are based on the SPARC architecture. So this Niagara or the UltraSPARC is also a SPARC based processor where you have 8 64-bit multi-threaded SPARC cores. So you can see the 8 cores, SPARC Core 0 up to SPARC Core 7. You have a shared 3 MB L2 cache. You have a 16 KB instruction cache per core and 8 KB data cache per core. There are 4 144-bit DDR2 DRAM interfaces. There is a 3.2 gigabits per second JBus I/O for I/O operations. The cryptographic algorithm that is used is it implements RSA, the public key RSA algorithm. There is extensive support for the RAS features, reliability, availability and serviceability, and the technology details are given here. If you look at the architecture of the UltraSPARC T1, so UltraSPARC T1 or Niagara, we will use it interchangeably because UltraSPARC T1 is codenamed as Niagara 1 and UltraSPARC T2 was codenamed as Niagara 2. So we will use these names interchangeably. So if you look at the architecture of UltraSPARC T1, you can find that there are 8 SPARC cores and there are 4 L2 banks. L2 is shared, whereas L1 is specific to each of these cores. And then you have the 4 DRAM controllers and you have them connecting to your main memory, and you have a crossbar interface here which connects these cores to the L2 banks. So this is the main architecture of UltraSPARC. And as I told you initially, this was basically designed as a server to handle multi-threaded applications. So each of these SPARC cores will support 4 threads of execution, and with 8 cores you can have support for 32 cores. And the basic idea was that to have zero context thread switching, zero cycle thread switching. So when you switch from one thread to another thread, the overhead that you have should be 0 cycles. So it is a 0 cycle thread switching that happens when you have a multi-threaded architecture like this. So if you look at the SPARC core here, each of these SPARC cores, they have some units which are dedicated to each core, some units which are shared between the various cores of the processor. So if you look at a SPARC core here, it has the following units supporting the pipeline. You have an instruction fetch unit which does the fetch operation, which does the thread select operation, deciding which thread is to be executed in that clock cycle. It controls the decode operation. It has the I-cache complex there. Then you have the execution unit where it consists of an ALU and a shifter unit for execution purposes. You have a multiply unit. You have a load store unit which takes care of all your memory and the write back operations, which is called your D-cache complex, which also holds your memory management unit. Then you have your thread logic unit, you have your floating point unit, and a SPU, which is a streaming processing unit. So this forms part of the core. So some of these units are exclusively available for each and every core as indicated there, whereas some of these units are shared across the various cores. For example, if you look at the floating point unit, the floating point unit initially was shared among the various cores, even the stream processing unit. So if you look at the high level block diagram of a core, this diagram shows you the high level block diagram of the core. There was hardware support for 4 threads. Hardware thread is also called a strand. That's why in the diagrams you see a strand instruction register and all that. So a hardware thread is also called a strand. So if you look at the hardware support for 4 threads, there are full register files with 8 register windows per thread. There is an address space identifiers. You have ancillary state registers and privileged registers. All of these are replicated for every thread. You have a shared L1 cache with a 16 KB instruction cache and a 8 KB data cache, and of course you have a shared TLB. So this shows you the execution pipeline. So as in the MIPS architecture, the MIPS architecture had a fetch, decode, and execute, a memory, and a write back. So the only extra stage that is brought in is a thread select stage in the second stage. So that is your thread select. So this, as I mentioned earlier, it's a very simple pipeline having 6 stages: fetch, thread select, decode, execute, memory, and write back. So during the fetch stage, the instruction gets fetched and then it moves on to the decode stage. So as you can see the diagram here, you find that thread select is controlled by means of this is the thread select logic here. So the thread is selected based on all these factors: the instruction type, whatever operation is happening, whether it is a long latency instruction or it will finish early, whether a trap has been generated or not. So it depends on all these, whether there is a structural hazard, there is a conflict between the various instructions. So based on all this, the thread select logic selects one of the thread for execution. And as you can see here, that information is given here as well as to the decode unit. So the decode unit, which instruction goes into the decode stage, will also depend upon the thread select logic. At the same time, that information is also given to the instruction cache wherein it is fetched. So any instruction that is taken out of that queue and it is decoded, you replace one more instruction for the thread by going ahead and fetching an instruction from the same thread. So all these are replicated information. So you have PC, which is connected to each of these threads. For every thread you have a separate PC. For every thread you have your D caches, you have 4 units here. So whatever has been register file, you have 4 units here. So whatever has been replicated for every thread, that has been indicated here. Your instruction buffer is also 4 for each and every thread. So that is the basic pipeline here. So the instruction gets fetched, it moves into the instruction buffer. So you have 4 streams of execution depending upon the 4 threads. one of them will get selected based on the thread select logic based on various conditions as I mentioned here. So, that will go into the decode process, and once an instruction is removed from that instruction buffer and moves on to the decode stage, you also try to fill in that slot by fetching another instruction from the same thread. And of course, you have the execution units here. You may have to access the data cache depending upon the type of the instruction, all that is the same. So, execution depends on what operation has to be done. Memory access depends on whether you have to perform a memory access or not, if it is a load or store instruction. Write back of course is writing into the register file. So, this gives you a brief idea of the execution pipeline. Going into a little more details of your instruction fetch unit. So, the instruction fetch unit, you have an MIL unit which is used to store the addresses that missed in the iCache and the ITLB. It feeds into the load store unit for further processing. You can basically fetch 2 instructions every clock cycle, and you have your instruction register which consists of your TIR and NIR, and the thread selector selects a valid instruction from the instruction register TIR. One PC and the next PC register are there for every thread, and the last retired PC is stored in your TLU, thread logic unit. So, thread selection policy, you have 5 states which are used here: a ready state, a run state, a speculative ready state, a speculative run state, and a wait state. So, thread switching, as I already mentioned, this is a fine grained threading that is used here. So, thread switching occurs at every clock cycle. Threads in one of these 5 states are scheduled according to the thread selector. Priority is given to the least recently executed available thread. So, you are not waiting due to long latency operations. You do not wait if there is an instruction cache miss occurring. You do not wait if there are traps. You do not wait if there are any resource conflicts. And priorities of threads in each state is according to this sequence that is given. And within idle threads, the priority goes this way. T0 has a higher priority than T1, than T2, than T3. This is the thread selection policy. Next, you go to the decode stage. The instruction fetch unit decodes the instructions. The FFU decodes the floating point instructions. FFU is your floating point functional unit. Privileges, whether you are operating in the supervisor mode of operation or you are working in the hypervisor mode of operation, if you are looking at virtual mode of operation, are checked in the decode stage itself. The branch condition is also evaluated in the decode stage, and in order to handle errors, you have parity which is given for your iCache and the T arrays, tag arrays. Parity is checked there. ITLB is parity decoded without error correction mechanism, and you also have a shadow scan support where the critical states, the PC, the thread state and MIL can be snapped and scanned out online. If you look at the execution unit here, there are basically 4 units. You have an ALU, you have a shifter, you have an IMUL unit which is a multiplier unit, and you have the divider unit. The ALU basically takes care of all your addition, subtraction, and other logical operations. Then you have your ECL unit as indicated here, which controls the multiplexers. As you can see here, it controls all the multiplexers here depending upon the opcode. So, depending on the opcode, it decides which functional unit is to be activated. So, it controls the multiplexers, it keeps track of threads and reads of instructions, it implements the bypass logic, it also write enables for your IRF. So, if you look at the L1 cache, instruction cache, which is private to each of these cores, it is 4-way set associative with 16 KB of data. It has a cache line size of 32 bytes. L1 data array has a single port. The tag array also has a single port. A valid bit array indicates the cache line state, and the replacement policy that is used is a pseudo random, and read access has higher priority over write accesses. Now, all these terms should be familiar to you because we have already done the basics of all this. The next is a stream processing unit. You have support for asymmetric cryptographic operations because you have a public key RSA which is implemented for up to 2048 bit key size. It supports modular arithmetic operations by sharing integer multiplier with the execution unit. It supports full modular exponentiation. The CPU initiates streaming load or streaming store operations to the level 2 cache L2 and compute operations to the integer multiplier. So if you look at the CPU cache crossbar here, so you can see that the various cores of your SPARC processor, the Ultra SPARC processor or the Niagara, are connected to your L2 cache through the crossbar. So you have 8 SPARC cores, 4 L2 cache banks, and IOB and floating point unit all interface with only the crossbar. And this is basically divided into two types, CPX and PCX, depending on whether you want to take data into the cores or you want to take data out of the cores. And each requester queues up to 2 packets per destination. It's a centralized arbitration which is happening with the oldest requester getting priority. So if you look at the PCX and CPX here, communication of data from the core to the units outside the core. So you have 5 arbiters here, arbiter 0 for L2 cache bank 0, arbiter 1 for L2 cache bank 1, arbiter 2 for bank 2, arbiter 3 for bank 3, and arbiter 4 for the floating point unit and the IO bus, and the transfer rate is 124 bits. Communicating data from the outside units to the core, you have 8 arbiters, arbiter 0 through 7, 8 arbiters because you have 8 cores, and it is 145 bits. And if you look at the TLU, which is the trap logic unit, it supports 6 trap levels. It can be in any one of the following modes. It is a reset error debug mode, which is a red mode. It is a hypervisor mode where you are trying to go in for virtualization support. It is a supervisor mode, and it is a user mode. So user mode, supervisor mode we are already familiar with. So depending on certain privileged operations which will have to be done only in the supervisor mode, you will have to switch to the supervisor mode. Hypervisor mode is when you are looking at a virtual machine implementation. And a trap causes the entire SPARC core pipeline to flush, and a thread switch occurs depending on what trap occurred until the trap vector is resolved. That is a normal case that happens in any pipeline. So whenever you have an interrupt coming in, the pipeline will have to be flushed. You will have to stop operation there, the pipeline will have to be flushed, a thread switch will occur, and depending on which caused a trap, the reason of the trap, you will have to take necessary action. So that is why we say until the trap vector is resolved, you will have to wait. The floating point unit, implements a SPARC floating point instruction set with a few exceptions. It is a single shared resource on the OpenSPARC T1 processor. Because initially when the OpenSPARC T1 processor or the Niagara processor was invented, it was not intended to be used for scientific computing where you are going to come across many floating point operations. It was basically intended to be used as a server to handle commercial services, commercial servers. So where you do not come across too many floating point operations, it is more of transactions that are going to happening. So we had only one floating point unit which was shared among the various cores. And each core can have one outstanding floating point instruction. The thread stalls if at all you have a problem there, waiting for the FPU result, the thread stalls and switches out this core for consideration in the when you do a thread select operation. The FRF, the floating point register file, and the FSR, the floating point state register, are not physically located within the FPU. It includes 3 parallel pipelines that can run instructions simultaneously at various stages of the pipeline. The instructions that can be executed are floating point add, floating point multiply, and floating point divide. Now moving out of the execution units, if you look at the DRAM interface to your main memory, you have 4 independent DRAM controllers. Each controller is connected to one of the L2 cache banks and one DDR2 memory channel. The DRAM controller services L2 cache requests from the DIMMs. The DRAM controller performs L2 cache write-backs to the DIMMs, and it supports DRAM power throttling by reducing the number of DIMM activations. Now looking at the L2 cache, we have already mentioned that the L2 cache is 3 MB in size. It maintains on-chip coherency across all L1 caches. It keeps a copy of all L1 tags in a directory structure, and that is how it maintains the coherence. There is no L3 cache, so no off-chip cache coherency that is needed. Coherency with only main memory is essential, and each L2 bank has a dedicated DRAM channel. So L1 cache is private to each and every core. L2 cache is shared across the various cores. Apart from the L2 cache, you only have the main memory. So, if you look at the highlights of the memory system, there is no external chipset because of the 4 on-chip memory controllers. So, you do not have an external chipset. Because of this, it becomes much faster and with a transfer rate of about 20 gigabytes per second as against 6.4 gigabytes per second that would have otherwise been possible. And the shared L2 cache I already mentioned, it eliminates snooping and it provides a unified address space to the operating system. And the crossbar enables 8 simultaneous memory addresses per cycle, 1 per core. So, that was the basics about the Niagara 1 processor. To give you a comparison between the Niagara 1 processor and the Niagara 2 processor, which basically has the same type of architecture, it is only the number of threads that you have a difference. In the case of Niagara 1, we had only 32 threads because you had 8 cores and 4 threads per core, so it was 32 threads. Whereas here you have 8 threads per core, so with 8 cores you have 64 threads, so double the number of threads per core, double the number of execution units per core, because obviously with more number of threads you need to provide more execution units, so you have more number of execution units, and you also have a new pipeline stage pick which picks 2 out of 8 threads to issue in a cycle. And the memory hierarchy, it's doubled set associativity of L1 from 4 to 8. It doubled the number of L2 cache banks from 4 to 8. Now there it is 1 per core, it boosts performance 18% over just 4 banks from 12-way to 16-way set associative. And if you look at the floating point unit, as I already mentioned, initially it was only 1 for the entire cores. All of them were sharing 1 unit, whereas in Niagara 2 you have 1 per core rather than 1 per chip, and it turned Niagara 2 into a very respectable chip even for scientific computing applications. And if you look at the latest SPARC processors, SPARC T4 was released in late 2001. Hot chips, the announcement for 16-core SPARC T5 CMT processor happened in 2012, and Oracle had told that its SPARC server processor roadmap in August 2010 that it will deliver a 128 physical CPU core which can handle up to 16,384 threads at the same time by 2015. And we have what we have today is latest of the SPARC processors, though they have not really achieved that many number of threads of execution. And the most important aspect of your Niagara processors is that it is open source. The entire T1 architecture is available open source as an RTL, T1 and T2 architecture. So, anybody who wants to innovate on this, you can just download this RTL and you can do modifications like adding cores, deleting cores, what will happen if you change the cache hierarchy. So, all this can be innovated because it is open source. So, that is the first architecture that we look at. The second architecture is IBM's CellBE architecture. Of course, this architecture was a joint effort by Sony, IBM and Toshiba, and this is an example of a heterogeneous architecture first of all. Whereas in the case of our Intel as well as the UltraSPARC processor that we looked at, they were examples of homogeneous processors where all the cores were of identical type. Whereas here the CellBE is a heterogeneous processor. It is heterogeneous because it has 1 power processing element and you have 8 synergistic processing elements. So, 1 core is going to be different, so it becomes a heterogeneous processor. And in order to provide connectivity among the various SPEs and connectivity between the PPE and the SPEs, you have an element interconnect bus. You have a direct memory access controller because you will have to feed to all the 8 processors. You have an extensive DMA transfer happening here. You have 2 Rambus XDR memory controllers and you have a Rambus Flex IO input-output interface. So, this is the architecture of your CellBE architecture. So, as I already mentioned, you have a power processing unit which acts as the control processor, and you have 8 SPEs which are basically used for exploiting the data level parallelism. You have an element interconnect bus which tries to interconnect the cores among themselves, the SPEs among themselves and with the main power processing unit. You also have the IO controllers and the memory controllers which will help you connect with the external memory and your IO devices. So, if you look at the power processing element, It is a 64-bit power architecture processor with 512K cache. It is a dual issue processor, dual threaded, but it is an in-order processor. And the control unit, it serves as the control unit for the SPEs. It runs the operating system and most of the applications, but the compute intensive parts of the OS and the applications will be offloaded to the SPEs. Because you have 8 SPEs, they basically take care of the data level parallelism, and it is basically a RISC architecture, and it uses considerably less power than other PowerPC devices even at higher clock rates. So, this gives you the major units of your power processing unit. Most of the units you should be able to identify. So, this is the vector processing unit and the floating point unit, this is the integer unit and your load store unit. This of course is your fetch unit and all that. So, most of these units you should be able to identify. So, if you look at the PPE pipeline, this gives you a view of the power processing unit pipeline. So, if you look at the synergistic processing elements, that again is dual issue, 128-bit 4-way SIMD. So, that supports vector processing. There are 4 integer units and 4 floating point units. You can basically do 8-bit operations or 16-bit operations or 32-bit operations if it is an integer operation, and if it is a floating point operation you can do 32-bit as well as 64-bit floating point operations. You have registers, 128-bit registers. You have a local store which is a specially designed local store. So, you have a 256 KB local store memory, local store which is available with each and every synergistic processing element. You do not have caches. So, these local stores are basically used as caches. They hold both the instructions as well as the data for that particular SPE. So, they are coherent and cooperative offload engines for the CPU. They work independently. They are not directly tied to the CPU as coprocessor. They have a dedicated DMA engine which moves data between the CPU, which is your power processing element, and the SPE or among the various SPEs. You can have parallel or serial transfer with other SPEs. So, this gives you the block diagram of the SPE indicating all the various functional units including the local store unit. And this is the SPE pipeline which tells you how many clock cycles each one of these will take. Remember, it is an in-order scheduling. So, you can see the number of clock cycles each one of these instructions take. And if you look at the SPE local stores, it is a 256 kilobyte local store, 1 per synergistic processing element. The SPEs operate on registers which are read from or written to the local stores. The local store can access main memory in blocks of 1 KB minimum and 16 KB maximum, but the SPEs cannot act directly on main memory. They can only move data to or from the local stores. And caches can deliver similar or even faster data rates, but in only very short bursts, a couple of 100 cycles at best. Whereas the local store can each deliver data at this rate continually for over 10,000 clock cycles without going to RAM. So, this is the element interconnect bus. So, it is basically a data ring for internal communication. You can have 4 16-byte data rings. It gives low latency for communication, and you can also have multiple simultaneous transfers. That peak bandwidth is 96 bytes per cycle peak bandwidth, which is about at the rate of half of the CPU speed. So, if you look at the cell characteristics, a big difference in cells from the normal CPUs, synergistic processing elements in a cell to be chained together to act as a stream processor. So, this gives you an example of how all of these cell processors, cell units, SPEs can be chained together to do streaming processing. So, the various operations that will have to happen in a stream processing application, you can see that they are given to each of these SPE units, and it is a chaining, it is like a pipeline getting formed there. So, you have a chaining operation that is getting done. So, they are very suitable for such types of applications. So, if you look at the memory and I/O, there is an external memory bus licensed from Rambus. You have a dual XDR interface with 25.6 gigabytes per second. External I/O is again licensed from Rambus, and you have a Flex I/O interface. So, you have a total of 76.8 gigabytes per second. Excessive shielding is necessary. So, you have a number of VDD and ground pins. And as far as the cell architecture is concerned, it tries to exploit parallelism, application level parallelism at different levels. The data level parallelism is exploited because of the SMD instruction support and the SPEs that you have. And each of these SPEs support in order scheduling, and they can have 2 threads per execution. So, you have ILP also getting exploited. So, ILP with static scheduling and power aware microarchitecture, and because of the compute operations happening parallelly along with the transfers that can happen on your DMA, you also have compute transfer parallelism, and there is also thread level parallelism support because you can have multiple threads of execution, because it is basically a multi-core. So, you can have support for multiple threads of execution, and you also have support for hardware multi-threading. And memory level parallelism, because you can overlap the transfers from multiple requests per core and also from multiple cores. So, if you look at other multiprocessors from IBM, you have Power 4, the world's first non-embedded dual core processor, which was released in 2001. Power 5 came in 2004, Power 6 in 2010, Power 7 which has implementation as a quad core, a 6 core and an 8 core processor, released in 2010, and the PowerPC 970MP dual core processor used in the Apple Power Mac G5, Xenon, which was later given. This is the architecture of the IBM Power 4 to give you an idea of what this architecture is. This is Power 5, Power 7, which was released in February 2010. And if you look at Power 7 and SMT, it has support for simultaneous multi-threading. You can either have SMT2 or SMT4 modes, and all these register renaming and all that I think you are already familiar with. So, applications of the Cell BE. Cell BE was basically brought in by IBM, Toshiba and Sony in order to have support for their gaming applications. So, the cell design was based on the analysis of a broad range of workloads in areas such as cryptography, graphics transformation and lighting, physics, FFTs, matrix operations and scientific workloads. So, the cell process is designed for graphics and network intensive jobs ranging from video games to complex imaging for the medical, defense, automotive and aerospace industries. So, you can see a lot of applications in these areas, including digits, writes, movements, and they are also used for scientific calculations, supercomputing. They can also act as servers and used for stream processing applications. So, these are the references, and all the figures have been taken from these references. So, to summarize, we have looked at 2 different styles of multi-core architectures. We have looked at the UltraSPARC architecture, which is basically a homogeneous type of architecture. It is highly multi-threaded. It was basically brought in order to handle server applications, and it is again a power efficient architecture. The second style of architecture that we looked at was the IBM Cell BE, which is basically a heterogeneous architecture which was built for gaming applications, and you can see that it exploits different types of parallelism. Thank you.